Alright, so we have another video coming. So this is the second video in the series. So first let's start by dealing with some unmentioned thing last time. So remember that in Lambda Calculus everything is a machine, and when we say apply f to x, you might think of f as being the active machine and x as the passive input. But this might not be the case because x is also a machine and its role is as active as that of f. So for example, we have id applied to true. Let's see what it does. Yep, I don't know why that's so slow. So you might now think that id is a machine and true as the data, but the reverse can happen, you know. We can apply true to id and that still works. See, still works. So yeah, you can't really distinguish between functions and their inputs. That's all I want to say. So let's go with something new. We have multiple arguments. So first of all, what is that? So multiple arguments is a notation. We have to apply a method to multiple arguments simultaneously instead of one at a time. The reason why is that it shows the intention better. What that means, I'll explain later. So these are the two versions of the same program. So this is the single argument version and this is the multiple arguments version. So in the single argument version, we must supply arguments in two steps. And in the multiple arguments version, we apply to both a and b at the same time, like that. Yeah. So that's that. Now I'm gonna argue why that is. This addition to the language is very necessary, even though it doesn't do anything new, right? It just changes how things are written. So for example, this program can be read in two ways. The first way is to group the first application and then apply to the other one, and the second one is that we apply this function id to both true and false at the same time. So yeah, it's not really clear if we only have one argument whether this means that this applies to both at the same time, or this applies to that and then take the result and then apply to that, right? So let's see what it does. So in this case, it's very clear that we want the version on the left here, because this function only accepts a single argument. So next we have Boolean logic. So the goal in implementing Boolean logic is the if expression. If xab is read as if a is true, then return a, otherwise return b. More specifically, we need these to be true. If xab will reduce to a when x is true, and if xab reduces to b whenever x is false. So again, these are the true and false function. I'm gonna use the multiple arguments version. So this is how we write if true ab. So we have the test boolean right here. This is the conditional, and we have two vertical bars. The green one indicates the true alternative and the red one indicates the false alternative. And let's see how it works. Yep. So it works like that. So notice that the if expression will just reduce to an application of the test boolean to the two arguments we have, like that. Yep. And then A and B will go there, then it returns A as expected. So note that sometimes an expression can be displayed differently from usual, like the if you just saw in the previous slide. So this is called visual sugar, which is just a way to help us poor humans read the program, right? The machine doesn't care how the program is written. So if you know language design, this is called syntactic sugar in normal programming languages. And worry not, so you might think that things are gonna get more complicated since I'm adding more things to the language, but the basic form of an expression will always be displayed when it is executed. So don't worry, I'm not gonna slide anything under you. So this is the other case, right? If false A, B. Note the name here. We have a name for the false function. So the name is just like a visual sugar again, but we use text instead of drawing some things. Yep. So again, you see that if expands to an application false applied to A and B, and what is false? False is this program right here. Yep. Then we can apply it. Yep. And as expected, it returns the other one, returns B. So with that out of the way, let's write some Boolean functions. First of all, we have the function AND, meaning that both must be true. More specifically, AND A and B means the following. If A is true, then if B is true, then we return true, and if B is false, then we return false. Otherwise, if B is false, then we return false. As an exercise, see how you can simplify this program. If you want to solve it, you can pause the video because I'm gonna show in the next slide. Alright, so this is the solution. So you accept two arguments. If the first one is true, then you return the second argument, and if the first one is false, then you returns false. So let's test it out, shall we? And true should return true. And indeed it does return true. Then we have and true false should return false. Let's see what it does. Yep, should return false. Yes, okay. Next we have the final case, and false false. See what it does. Should return false also. Yep. Expand the if, expand the false, and then we have false. Yep. Alright. So we have and. Now we have OR. So OR AB means that when A is true, we return true. When A is false, then when B is true, we return true. When B is false, we return false. So again, try to simplify this program. I'm gonna show you in 3, 2, 1. Bam. So similarly, this program can be written as if the first argument is true, then we return true. Otherwise, if the first argument is false, then we return the second argument. Pretty simple. Let's test it out. All true should return true. Yep, spend the true. Yeah, should return true. Okay. We have all true false should return, guess it, true. See if we write, spend the or, true and false, then we spend the if, spend true. Yep, it returns true. Next we have all false false. What should it return? False. See if I'm right. Yeah, indeed, it does return false. Alright, so now we're done with Boolean. Let's go to the halting problem. So we have a question, right? Is it possible for parts of a program to be non-terminating, but as a whole it still terminates? So with branching, it allows us to derive such a program. So this example I call the contagious loop. We have and applied to true and loop. So you remember that from the previous video, this expression is gonna loop forever, consuming all of your CPU till the end of time. See what it does. Yep. Okay, it loops forever and ever and ever and ever. It's just gonna loop forever. Alright, but the loop is not inevitable, right? So this is the same example as before, but I've replaced the and with the or. Let's see if it's gonna loop again. And oh, surprisingly it doesn't loop. So what happens? So what happened is that because there's a branching right here, right? It's gonna choose whether to evaluate this one or this one. Because we have true right here, this loop is never gonna be reduced. Sorry. Let's go back. So this loop is never gonna be reduced, only this will be returned, right? Yep, true. It only, yep, see right here, this argument is never gonna be referred to in the body, only the first argument will be passed down in the body. Yep, it is appear. Okay, and that's how it works. Pretty neat, huh? So what did we learn? We learned that it's not obvious to know whether a program will terminate, even if we know exactly what it does. In fact, it's impossible to know in general. Now is the end. You have some exercise. We have negation, so not A will return true when A is false, and it will return false when A is true. And then the exclusive OR function is true when one and only one of its arguments is true. And then try to write the ternary function. The AND ABC is true when all of its arguments are true, and the OR ABC is true when either A, B, or C is true. Can you implement the ternary operators in terms of the binary ones? And what about quaternary and quinary functions? As you do that, can you see a pattern? Alright, and that's it. Credits roll.